Welcome to a new deep dive. You look at a robotic arm and you see this perfect mathematical motion.
Yeah, you assume you put a specific amount of energy in, and you get exactly that much motion out.
Right. But look closely at the engineering data on its harmonic drives, and you realize that mathematical purity is basically a lie.
It really is. Inside, it's just a messy thermodynamic war zone.
And today's deep dive unpacks an engineering presentation on exactly that. We're looking at these incredibly compact, ultra-precise gears.
Right. We want to look at the exact vocabulary of that resistance, really isolating the mechanical forces that prevent true efficiency.
So if a blueprint says 100 watts goes in, we know 100 watts of work isn't actually happening.
No, not at all.
If I'm feeding power into this closed system, what kind of physics tax is being collected before the machine even does its job?
Well, the data shows that even in a high-end harmonic drive, mechanical efficiency is usually trapped between, say, 70 and 90%.
Wait, really? So up to 30% is just gone?
Exactly. That cut is absorbed directly by the materials. The core of a harmonic drive relies on a flex spline.
A flex spline?
Yeah, it's this flexible metal gear cup that has to continuously deform to engage the outer gear.
Like it physically bends?
Yes, constantly. And physically bending that metal creates massive internal molecular friction. Factor in the tooth sliding and the bearing roll, and, well, that input energy is simply consumed by the structure itself.
Okay, but that friction comes from actually doing work, right? Like bending metal and moving parts under power.
Right.
But I'd imagine just, forcing lubricant through tight spaces before the motor even warms up introduces an entirely different kind of resistance.
Oh, absolutely. Engineers categorize this as no-load running torque.
No-load running torque.
Yeah, it's a raw twisting force required just to spin the input shaft when absolutely zero payload is attached.
Huh.
R&D teams actually stress test this at sub-zero temperatures to calculate the motor's starting margin. They have to guarantee the drive won't stall out against its own stiffened grease and tight vacuum seals.
Man, so it's like trying to stir a jar of cold peanut butter. You're exhausted before you've even started baking.
That is a perfect analogy. Or like trying to run in waist-deep water.
Right. And I assume it gets worse as you accelerate. Like the faster you try to move through that fluid, the harder the grease fights back.
Yeah, that phenomenon is called viscous drag. As the machine speeds up, the sheer force of the grease-resisting high-speed movement actively tanks the system's efficiency.
Is there a way around that?
Well, the standard R&D fix is swapping to a lower viscosity synthetic grease. You use a chemically engineered thinner fluid to maintain low drag at higher operational speeds.
Let me push back on that, though.
Sure.
If thinner grease solves viscous drag, why not just use the thinnest synthetic oil available? Doesn't that invite, metal-on-metal destruction the second you actually attach a heavy payload?
That is the exact trade-off causing load-dependent loss.
Okay, what does that mean?
When you spike the output torque, say the drive is suddenly lifting a massive robotic payload, the pressure on those microscopic gear teeth skyrockets.
And if the grease is too thin, it just gets crushed out of the way.
Precisely. It simply shears apart under that pressure. So to compensate, developers are constantly experimenting with advanced tooth surface coatings.
Oh, I see.
Yeah, they have to treat the metal surface itself to survive extreme friction without relying entirely on the fluid barrier.
Because if that friction goes unchecked, we aren't just losing efficiency points on a chart, we are generating internal friction heat. The energy doesn't just vanish.
Right, and in a tightly packed system, like a harmonic drive, heat is fatal.
Fatal.
Yeah, if the internal flex spline gets too hot, the metal physically expands outward.
Wait, the cup actually gets bigger?
Yes, just a few extra microns of thermal swelling, and it violently binds against the rigid outer gear, the circular spline.
Wow, so the drive literally swells up and chokes itself? That is wild.
It is. It forces you to realize that every millimeter of smooth motion is a hard-fought victory against systemic resistance.
Unbelievable. So if you're designing with these systems, knowing these thermal bottlenecks completely changes how you spec your load limits.
Exactly.
You have to account for these microscopic forces in everything you build.
Whether you are building robotics or just curious about how things work, knowing these terms helps you appreciate the invisible battles against friction happening inside every single device you use.
Consider this. We spend millions engineering the absolute perfect mechanical teeth for these drives, only to have the system's physical limit dictated by the chemical behavior of a few drops of grease.
Right.
The very fluid required to lubricate the gears and stop them from grinding themselves to dust is the exact same fluid causing the viscous drag and the heat that threatens to destroy the system.
It's the ultimate engineering irony.
It really is. Next time you spec a motor, ask yourself, are you really engineering the metal, or are you just managing the fluid?